The third and final type of polarization that we're going to discuss in this class is TM polarization. That stands for transverse magnetic polarization, and this is when the H field is parallel to the plane of incidence. So here we see that we've got a propagating field coming in here. It's incident. H is parallel to this field. E, on the other hand, is not. E will form some angle with this surface. Since only the magnetic component is transverse, we call that the TM mode. And like the TE mode, we have to adjust our equations of incident, reflection, and transmission to account for this mode. And so I'll just get into that. The incident wave is equal to E0 I e to the minus j beta 1 cosine of, sorry, not cosine, it's x sine of the angle of incidence plus z cosine times the angle of incidence. And we have to adjust for the fact that this doesn't point purely in the x or the z direction, but a little bit in both. And so we need to multiply this by cosine theta I a hat x minus sine theta I a hat z. So that accounts for the fact that it's no longer parallel. So that's the incident wave for the the electric field component. The incident wave for the electric field component is equal to E0I over eta. So looking very familiar. E to the minus j beta 1 x sine theta I plus z cosine theta I. And we can see that the magnetic field is pointing from this picture in the y direction. We have similar equations for the reflected waves. ESR is equal to E0R e to the minus j beta 1 x sine theta R minus z cosine theta R. And we have to account for the fact that magnetic field's not in either the x or the z plane, but exists a little bit in both. So that's cosine theta R a hat x plus sine of theta R a hat z. So that takes care of the electric field. The magnetic field is HSR is equal to minus E0R over eta e to the minus j beta 1 x sine of theta R minus z cosine of theta R a hat y. We've got to be careful here. There is a minus sign for the TM mode. That's because it doesn't get absorbed into the unit vectors here, like it did in the TE case. Now we have to write our equations for the transmitted portion. Transmitted electric field is E0T e to the minus j beta 1 times x sine theta t plus z cosine theta t. And then that's going to be in the cosine theta t a hat x minus sine theta t a hat y. And then finally, the transmitted magnetic field is equal to E0t divided by eta 2. Oop, I made a mistake here, that's beta 2. E to minus j beta 2 x sine angle of the transmitted wave plus the cosine angle of the transmitted wave. That's pointing in the a hat y direction. we can relate E0I and E0R and E0I and E0T through the reflection and transmission coefficients for the TM mode. And so that is just going to be E0R is equal to the reflection coefficient of the TM mode times E0I. And the new formula we have for the TM mode reflection coefficient is N2 cosine of theta t minus N1 cosine of theta I over N2 cosine theta t plus N1 cosine of theta I, and the magnitude and angle of the transmitted electric field is equal to tau for the TM mode times the magnitude and phase of the incident magnetic or electric field. And that is necessarily, we're going to have to calculate tau here. That's equal to 1 plus the reflection coefficient Tm times cosine of theta I, the ratio of cosine theta I to cosine theta t. And so that gives us our TM polarization calculations. For the TM wave, we still have to calculate the angle of incidence, the angle of reflection, and the angle of transmission. We can still use Snell's law to do that. So you use the exact same formulas that I showed for the TE mode, and you just apply those to the TM mode for angle of incidence and angle of transmission. Sorry, angle of reflection and angle of transmission. So just go back to Snell's law. However, the critical angle calculation is different, and for the TM mode, we don't have a critical angle anymore. We have what's called Brewster's angle. And Brewster's angle tells us what angle is required such that the entire TM wave is transmitted into media 2. So it's a little bit different. The critical angle tells us when entire reflection occurs in the TE mode, and Brewster's angle tells us when entire transmission occurs for the TM mode. So it's different. And Brewster's angle, we give the symbol theta sub BA for Brewster's angle, and it is equal to sine -1 of 1 over the square root of 1 plus the relative permittivity of media 1 over the relative permittivity of media 2. So we take the inverse sine of this, and if theta I is greater than Brewster's angle, then total transmission. Remember, that's only for the TM mode. So critical angle is only for TE. Brewster's angle is only for TM. Snell's law works for both Brewster's angle, or for both the TM mode and the TE mode.